In this video, let's discuss the geometric interpretations of the best estimation. The theorems we introduced earlier on multivariable Gaussian distributions can give geometric interpretations which have a strong intuitive appeal. To show this, let's consider two random variables, so x and y, so they are random vectors. Let's also introduce the vectors mu x and mu y. So mu x is x minus the mean of x. Mu y is y minus the mean of y. Therefore, the both vectors, so mu x and mu y, they have zero means. Now let's make some connections between the operations on probability space and operations on linear vector space. In linear vector space, the operations between two vectors is defined as the inner product. So the inner product between the mu x and mu y is defined as the expectation, the autocorrelation between mu x and mu y. So that's the expectation of mu x times mu y transpose. Then we know this is exactly the covariance of x and y. So therefore, the covariance between the random vectors x and y can be interpreted as the inner product between the vectors mu x and mu y. The norm of mu x is defined as the norm of mu x squared is defined as the inner product between mu x and mu x itself. So this is the covariance of the random vector x. The covariance of the random vector x can be interpreted as the norm of mu x. Let's define the angle in the linear vector space. So the angles between two vectors, so mu x and mu y, is defined in this way. So this is the inner product, so between mu x and mu y, weighted by the norm of mu x and mu y. Then we know this mu x and mu y, the inner product of mu x and mu y is a covariance between x and y. And the mu x is just the square root of the covariance of x. So mu y norm is square root of the covariance of y. So this is exactly the definition of autocorrelation coefficient we introduced earlier. So this is the autocorrelation coefficient between x and y. We know for the autocorrelation coefficient, its range is between -1. This is between -1 and 1. So this is exactly the range of cosine theta. Then we can define the angle between two vectors, so mu x and mu y. We know that in linear vector space, so the best representation of mu x in terms of mu y is the projection of mu x on mu y. Then the projection on linear vector space is like this. So the projection of mu x on mu y, so it is the inner product between mu x and mu y over mu y norm squared. Based on earlier definition, we know that the inner product of mu x and mu y is the covariance of between x and y. So this is the Rxy. If we use earlier notations, this is Rxy. So this is Rxy. So mu y is still mu y. Then the mu y norm square. So based on earlier definition, so the mu y norm square is the covariance of y itself. Is the auto covariance of y. So this is Ry. This is why we have this Rxy. So Ry inverse and mu y. Then we know based on early definitions, so this is, so based on the result of theorem 3.4, so this is the expectation of mu x conditional on mu y. So this is the theorem 3.4, because here the mu x and mu y, they have zero means, for example. So this is a mu x. So this is a mu x. This is a mu x. This is a mu y. Because it has a zero mean, so this mean is zero. So this will be mu y. So the expectation of mu x condition on mu y is just rxy, ry inverse mu y. So therefore, the projection of the vector mu x on mu y can be interpreted as the conditional expectation of mu x conditioned on mu y. Then let's define a vector z. Okay, the z, like z is defined as the difference between the x and the conditional mean of x conditional y. We know this is the x, the conditional mean is the best estimate of x. Then the difference between x and its estimation, so that's the estimation error. So the z is the estimation error. Then based on this relationship, the expectation of x condition y is the expectation of x plus the expectation of mu x condition mu y. So therefore, so the z is the mu x minus the expectation of mu x conditioned on mu y. So therefore, the z can also be considered as the estimation error of mu x between its estimate conditioned on mu y. Then we know that the conditional mean of mu x conditional on mu y, so it's rxy, ry inverse mu y. So this will be, z will be mu x minus rxy, ry inverse mu y. Then based on the theorem 3.3, we know z had a zero mean and is independent of y. So this is the definition of mu x and mu y. Then based on the result of 3.3, we know this z. So this is mu x. So this is a mu x. Then this is a mu y. This is a mu y. Then this part. So this part. So this part will be the expectation of mu x conditioned on mu y. Okay. So based on this result, we know this is z, so mu x minus the expectation of mu x condition on mu y is independent of y, has zero mean, So this is a covariance of mu x minus mu x, rx minus rxy, ry inverse ryx. Z is independent of y, so z has zero mean. So therefore, the covariance between z and y is zero. If the covariance is zero, then we know the inner product of the z and mu y. So inner product of z and mu y is zero. So the inner product is zero. So geometrically, it means the z is orthogonal to mu y. And also the z is the difference between mu x and its projection. So the projection here, so is the conditional expectation of mu x and mu y. Then we know this, the estimation error, so that the size of the covariance of the covariance of E, based on theorem 3.3, so covariance of Z will just be Rx minus Rxy, Ry inverse Rxy. It could be Rx minus Rxy, Ry inverse Rxy. We know that the covariance of the Z will be just the norm of Z squared. Then we know this mu x and the projection of mu x on mu y and Z, they form a right triangle because this Z is orthogonal to mu y, so this is a right triangle. Therefore, we can use the Pythagorean theorem. So the sides of Z is Rx minus Rxy, Ry inverse Rxy will be the size of mu x minus the size of the conditional expectation. And the size of mu x is mu x squared is also the covariance of x. Then the size of the projection should be the square of the inner product and square of mu y, then the square of the norm, square of mu y norm, and the square of mu y power 4 will be the norm square. Then also, so this one, okay, this inner product, the inner product between mu x and mu y will be just Rxy, Rxy. Then the mu y norm square will be just the inverse of Ry inverse. So therefore, the best estimate of x, so that is the conditional mean of x conditional y, so can be interpreted as geometrically as a projection of mu x on mu y. To interpret theorem 3.5, so this is 3.5, the mu, the u and v, so they're independent. To interpret theorem 3.5, we introduce a three-dimensional Euclidean space. As u and v are independent, therefore the corresponding vectors of the mu u and mu v are orthogonal. So they form the orthogonal basis along the direction of mu u and mu v. Then the result in theorem 3.5 is like this. So the expectation of the x conditioned on u and v is the expectation of x conditional u plus the expectation of x conditional v minus the expectation of x. So now let's so this is the result of the result of theorem 3.5. Now let's minus mu x on both sides of the equation. So minus mu x on both sides of the equation. Then based on this relationship, we know the conditional mean of x conditional y is the expectation of x plus the expectation of mu x conditional mu y. So therefore we know, so this one will be the expectation of mu x conditioned on mu u and mu v. Okay, so this will be the so this minus exponential x, okay, it will be the expectation of the mu x condition on the mu u and mu v. So this one will be the expectation of mu x condition on the mu u. The last one will be the expectation of mu x conditions on mu v. That this equation can be interpreted geometrically. Then the expectation of mu x condition of the mu u. So based on the earlier explanation, we know this is a projection. So this is the projection. So the expectation of mu x condition of mu u can be interpreted as the orthogonal projection of the mu x on mu u. So this is the conditional mean of the mu x condition of mu u. So that is the projection of the mu x on mu u. Then this conditional expectation of mu x condition on mu u is a projection of mu x on mu v. So this green line, so this is the expectation of mu x condition on mu v. So it's a projection of mu x onto mu v. And the expectation of mu x condition on the mu u and mu v, so can be considered as the projection of mu x onto the linear space, spanned by mu x and mu v. The projection of mu x on a two-dimensional subspace is the sum of the projection on an orthogonal basis in the sum space. So therefore, the expectation of the mu x conditional on mu u, mu v is the sum of the expectation of mu x conditional on mu v and the expectation of mu x over mu u. So this is the geometric interpretation of this formula, of this equation. The extension of these interpretations to higher dimensions is kind of straightforward. Notice that geometric interpretations depend on only in the properties of the first and second moment. This implies that it is not necessary to assume that the distributions are normal or Gaussian. And however, if the distribution is not Gaussian, the projection cannot be interpreted as conditional expectation. To give a probabilistic interpretation of the projections, we will use the projection theorem. The projection theorem is stated like this. So let y1, y2, and yl and x be elements in the Euclidean space. And let y be the linear space spanned by y1, y2, and yl. Then there exists a unique element x hat belong to y such that the norm, the distance between x and x hat, we can find this x hat to minimize the difference between the x and the linear space to any element in y. So y will be the linear space spanned by y1, y2, and y. So if we interpret it in the estimation problem, it's kind of like so y1, y2, yl, and x. So there are some random variables. Then we have some observations of y1, y2, and yl. Then what we want to estimate x, like say the information provided, what's the best information provided by y1, y2, and y about the information of x? Then we know, so this can be, so this is best estimate of x, so can be expressed as a linear combination of y1, y2, and y to minimize kind of like a mean square error. For random variables, so which are not normal, not Gaussian, so this projection cannot be interpreted as linear. This cannot be interpreted as projection, but they can be interpreted as linear estimates. So based on the observations, which minimizes the mean square error. So the best estimate is a linear estimate will minimize the mean square error. The projection can be interpreted as a linear estimate of x based on the observations y1, y2, yl, which minimizes the mean square error. Let me give you several remarks. For normal processes, the conditional mean is a linear function of yt. We can see from here, so the best from this result, so the best estimate of x conditioned on available information will be the expectation of x conditioned on each of them. Then for each of them, the conditional expectation is a linear function, of y, or the linear function of the available information. So therefore, for normal process, the conditional mean is a linear function of yt. Then the best estimate for normal processes, the best estimate is a linear function of observations for all loss functions which satisfy the condition of theorem 3.1. So this statement tells us even though we do not impose any constraints on the best estimator, it's turned out that the best estimator is linear. When signals and the noise processes are characterized as second-order stochastic process, then the best linear estimation problem, which minimize the mean square error, okay? When the noise and the signal process are not Gaussian, let's assume they're just second-order stochastic process. Therefore, the estimation problem can be formulated in this way. We want to minimize so that we know to completely specify an estimation problem, we need to specify the noise and signal processes. So in this case, so the noise and signal process are described by second-order processes. And the criterion which defines the best estimate is the mean square error. And we put some restrictions on the admissible estimator, so the estimator must be linear. So this is a problem formulation here. So the signal and the noise are characterized by the second-order stochastic processes. And the criterion to define the best estimate is to minimize the mean square error. And we also put some restrictions on the estimator. The estimator must be linear. If it is this case for this problem, then the best linear estimation is the same as the one with normal process, if you just assume is that the process, the second order process, is a Gaussian, is a normal process, then the best linear estimator is still the conditional mean. So the best estimate has had conditional mean of x, conditional y. Then we use the mu x, okay, so rxy, ry inverse y, and my. But then when they're not the normal process or Gaussian process, then we can use just the first and the second order moments to represent the mean and the covariance. So here is must be pay attention that. So here we put the linear constraints on the estimators. Okay? So if we remove these constraints for non-Gaussian process, then the best estimate may not be linear, may not be a linear function of all observations. But however, if we put the constraints, the estimator must be linear, then the best linear estimator has the same structure like the best estimator for normal processes. We just need to replace this mean and the covariance by first and second moments. Also note that, so for normal process, even though we do not impose any constraints on the estimators, then the best estimator is linear.